A barometer is a scientific instrument used in meteorology to measure atmospheric pressure, pressure tendency, and forecast short-term changes in the weather. Numerous measurements of air pressure are used within surface weather analysis to help find surface troughs, high-pressure systems, and frontal boundaries. Barometers and pressure altimeters are essentially the same instrument, but used for different purposes. An altimeter is intended to be transported from place to place, matching the atmospheric pressure to the corresponding altitude, while a barometer is kept stationary and measures subtle pressure changes caused by weather. The main exception to this is ships at sea, which can use a barometer because their elevation does not change due to the presence of weather systems. Aircraft altimeters may need to be adjusted as they fly between regions of varying normalized atmospheric pressure. History. Although Evangelista Torricelli is universally credited with inventing the barometer in 1643, historical documentation also suggests Gasparo Berti, an Italian mathematician and astronomer, unintentionally built a water barometer sometime between 1640 and 1643. French scientist and philosopher René Descartes described the design of an experiment to determine atmospheric pressure as early as 1631, but there is no evidence that he built a working barometer at the time. On July 27, 1630, Giovanni Battista Bagliani wrote a letter to Galileo Galilei explaining an experiment he had made in which a siphon, led over a hill about 21 meters high, failed to work. Galileo responded with an explanation of the phenomenon. He proposed that it was the power of a vacuum that held the water up, and at a certain height the amount of water simply became too much and the force could not hold anymore, like a cord that can support only so much weight. This was a restatement of the theory of hora vacui, which dates to Aristotle, and which Galileo restated as resistens del vacuo. Galileo's ideas reached Rome in December 1638. In his discourse, c. Raffaele Maggiotti and Gasparo Berti were excited by these ideas, and decided to seek a better way to attempt to produce a vacuum than with a siphon. Maggiotti devised such an experiment, and sometime between 1639 and 1641, Berti carried it out. 4 accounts of Berti's experiment exist, but a simple model of his experiment consisted of filling with water a long tube that he had both ends plugged, then standing the tube in a basin already full of water. The bottom end of the tube was opened, and water that had been inside of it poured out into the basin. However, only part of the water in the tube flowed out, and the level of the water inside the tube stayed at an exact level, which happened to be 10.3 meters, the same height Bagliani and Galileo had observed that was limited by the siphon. What was most important about this experiment was that the lowering water had left a space above it in the tube which had no intermediate contact with air to fill it up. This seemed to suggest the possibility of a vacuum existing in the space above the water. Torricelli, a friend and student of Galileo, interpreted the results of the experiments in a novel way. He proposed that the weight of the atmosphere, not an attracting force of the vacuum, held the water in the tube. In a letter to Michelangelo Ricci in 1644 concerning the experiments, he wrote, "Many have said that a vacuum does not exist, others that it does exist in spite of the repugnance of nature and with difficulty. I know of no one who has said that it exists without difficulty, and without a resistance from nature. I argued thus, if there can be found a manifest cause from which the resistance can be derived which is felt if we try to make a vacuum, it seems to me foolish to try to attribute to vacuum those operations which follow evidently from some other cause, and so by making some very easy calculations, I found that the cause assigned by me ought by itself alone to offer a greater resistance than it does when we try to produce a vacuum. It was traditionally thought that the air did not have lateral weight. That is, that the kilometers of air above the surface did not exert any weight on the bodies below it. Even Galileo had accepted the weightlessness of air as a simple truth. Torricelli questioned that assumption, and instead proposed that air had weight and that it was the latter which held up the column of water. He thought that the level the water stayed at was reflective of the force of the air's weight pushing on it. In other words, he viewed the barometer as a balance, an instrument for measurement, and because he was the first to view it this way, he is traditionally considered the inventor of the barometer. Because of rumors circulating in Torricelli's gossipy Italian neighborhood, which included that he was engaged in some form of sorcery or witchcraft, Torricelli realized he had to keep his experiment secret to avoid the risk of being arrested. He needed to use liquid that was heavier than water, and from his previous association and suggestions by Galileo, he deduced by using mercury. A shorter tube could be used. With mercury, which is about 14 times heavier than water, a tube only 80 centimeters was now needed, not 10.5 meters. In 1646, Blaise Pascal, along with Pierre Petit, had repeated and perfected Torricelli's experiment after hearing about it from Marin Mersenne, who himself had been shown the experiment by Torricelli toward the end of 1644. Pascal further devised an experiment to test the Aristotelian proposition that it was vapors from the liquid that filled the space in a barometer. His experiment compared water with wine, and since the latter was considered more spirituous, the Aristotelians expected the wine to stand lower. Pascal performed the experiment publicly, inviting the Aristotelians to predict the outcome beforehand. The Aristotelians predicted the wine would stand lower. It did not. However, Pascal went even further to test the mechanical theory. If, as suspected by mechanical philosophers like Torricelli and Pascal, air had lateral weight, the weight of the air would be less at higher altitudes. Therefore, Pascal wrote to his brother-in-law, Florent Perrier, who lived near a mountain called the Puy de Dôme, asking him to perform a crucial experiment. Perrier was to take a barometer up the Puy de Dôme and make measurements along the way of the height of the column of mercury. He was then to compare it to measurements taken at the foot of the mountain to see if those measurements taken higher up were in fact smaller. In September 1648, Perrier carefully and meticulously carried out the experiment and found that Pascal's predictions had been correct. The mercury barometer stood lower the higher one went. Types. Water-based barometers. The concept that decreasing atmospheric pressure predicts stormy weather, postulated by Lucien Vidi, provides the theoretical basis for a weather prediction device called a storm glass or a Goethe barometer. The French name Le Barometer Liégeois is used by some English speakers. This name reflects the origins of many early weather glasses, the glass blowers of Liège, Belgium. The weather ball barometer consists of a glass container with a sealed body, half filled with water. A narrow spout connects to the body below the water level and rises above the water level. The narrow spout is open to the atmosphere. When the air pressure is lower than it was at the time the body was sealed, the water level in the spout will rise above the water level in the body. When the air pressure is higher, the water level in the spout will drop below the water level in the body. A variation of this type of barometer can be easily made at home. Mercury barometers. A mercury barometer has a glass tube closed at one end with an open mercury-filled reservoir at the base. The weight of the mercury creates a vacuum in the top of the tube known as Torricellian vacuum. mercury in the tube adjusts until the weight of the mercury column balances the atmospheric force exerted on the reservoir. High atmospheric pressure places more force on the reservoir, forcing mercury higher in the column. Low pressure allows the mercury to drop to a lower level in the column by lowering the force placed on the reservoir. Since high temperature levels around the instrument will reduce the density of the mercury, the scale for reading the height of the mercury is adjusted to compensate for this effect. The tube has to be at least as long as the amount dipping in the mercury plus head space plus the maximum length of the column. Torricelli documented that the height of the mercury in a barometer changed slightly each day and concluded that this was due to the changing pressure in the atmosphere. He wrote, "We live submerged at the bottom of an ocean of elementary air, which is known by incontestable experiments to have weight. The mercury barometer's design gives rise to the expression of atmospheric pressure in inches or millimeters or feet. The pressure is quoted as the level of the mercury's height in the vertical column. Typically, atmospheric pressure is measured between 26.5 inches and 31.5 inches of Hg. 1 atmosphere is equivalent to 29.92 inches of mercury. Design changes to make the instrument more sensitive, simpler to read, and easier to transport resulted in variations such as the basin, siphon, wheel, cistern, Fortin, multiple folded, stereometric, and balance barometers. Fitzroy barometers combine the standard mercury barometer with a thermometer, as well as a guide of how to interpret pressure changes. Fortin barometers use a variable displacement mercury cistern, usually constructed with a thumb screw pressing on a leather diaphragm bottom. This compensates for displacement of mercury in the column with varying pressure. To use a Fortin barometer, the level of mercury is set to the zero level before the pressure is read on the column. Some models also employ a valve for closing the cistern, enabling the mercury column to be forced to the top of the column for transport. This prevents water hammer damage to the column in transit. On June 5, 2007, a European Union directive was enacted to restrict the sale of mercury, thus effectively ending the production of new mercury barometers in Europe. Vacuum pump oil barometer. Using vacuum pump oil as the working fluid in a barometer has led to the creation of the new world's tallest barometer in February 2013. The barometer at Portland State University uses doubly distilled vacuum pump oil and has a nominal height of 12.4 meters for the oil column height. Expected excursions are in the range of plus or minus 0.4 meters over the course of a year. Vacuum pump oil has very low vapor pressure and it is available in a range of densities. The lowest density vacuum oil was chosen for the PSU barometer to maximize the oil column height. Aneroid barometers. An aneroid barometer is an instrument for measuring pressure as a method that does not involve liquid. Invented in 1844 by French scientist Lucien Vidi, the aneroid barometer uses a small, flexible metal box called an aneroid cell, which is made from an alloy of beryllium and copper. The evacuated capsule is prevented from collapsing by a strong spring. Small changes in external air pressure cause the cell to expand or contract. This expansion and contraction drives mechanical levers such that the tiny movements of the capsule are amplified and displayed on the face of the aneroid barometer. Many models include a manually set needle which is used to mark the current measurement so a change can be seen. In addition, the mechanism is made deliberately stiff, so that tapping the barometer reveals whether the pressure is rising or falling as the pointer moves. This type of barometer is common in homes and in recreational boats, as well as small aircraft. It is also used in meteorology, mostly in barographs, and is a pressure instrument in radiosondes. Barographs. A barograph records a graph of atmospheric pressure. MEMS barometers. Microelectromechanical systems barometers are extremely small devices between 1 and 100 micrometers in size. They are created via photolithography or photochemical machining. Typical applications include miniaturized weather stations, electronic barometers and altimeters. More unusual barometers. There are many other more unusual types of barometer, from variations on the storm barometer, such as the Collins-Payton table barometer, to more traditional-looking designs such as Hooke's althiometer and the Rossum piezometer. Some, such as the shark oil barometer, work only in a certain temperature range, achieved in warmer climates. A barometer can also be found in smartphones such as the Samsung Galaxy Nexus, Samsung Galaxy S3, S6, Motorola Xoom and Apple iPhone 6 smartphones. Based on MEMS and piezo-resistive pressure sensing technologies, inclusion of barometers on smartphones was originally intended to provide a faster GPS lock. However, third-party researchers were unable to confirm additional GPS accuracy or lock speed due to barometric readings. The researchers suggest that the inclusion of barometers in smartphones may provide a solution to determining a user's elevation, but also suggest that several pitfalls must first be overcome. Applications: barometric pressure and a pressure tendency have been used in weather forecasting since the late 19th century. When used in combination with wind observations, reasonably accurate short-term forecasts can be made. Simultaneous barometric readings from across a network of weather stations allow maps of air pressure to be produced, which were the first form of the modern weather map when created in the 19th century. Isobars, lines of equal pressure, when drawn on such a map, give a contour map showing areas of high and low pressure. Localized high atmospheric pressure acts as a barrier to approaching weather systems, diverting their course. Atmospheric lift caused by low-level wind convergence into the surface low brings clouds and sometimes precipitation. The larger the change in pressure, especially if more than 3.5 hectopascals, the greater the change in weather that can be expected. If the pressure drop is rapid, a low-pressure system is approaching, and there is a greater chance of rain. Rapid pressure rises, such as in the wake of a cold front, are associated with improving weather conditions, such as clearing skies. With falling air pressure, gases trapped within the coal and deep mines can escape more freely. Thus, low pressure increases the risk of fire damp accumulating. Collieries therefore keep track of the pressure. In the case of the Trimden Grange colliery disaster of 1882, the mines inspector drew attention to the records and in the report stated, the conditions of atmosphere and temperature may be taken to have reached a dangerous point. Aneroid barometers are used in scuba diving. A submersible pressure gauge is used to keep track of the contents of the diver's air tank. Another gauge is used to measure the hydrostatic pressure, usually expressed as a depth of sea water. Either or both gauges may be replaced with electronic variants or a dive computer. Compensations. Temperature. The density of mercury will change with temperature, so a reading must be adjusted for the temperature of the instrument. For this purpose, a mercury thermometer is usually mounted on the instrument. Temperature compensation of an aneroid barometer is accomplished by including a bimetal element in the mechanical linkages. Aneroid barometers sold for domestic use typically have no compensation under the assumption that they will be used within a controlled room. Temperature range. Altitude. As the air pressure decreases at altitudes above sea level, the uncorrected reading of the barometer will depend on its location. The reading is then adjusted to an equivalent sea level pressure for purposes of reporting. For example, if a barometer located at sea level and under fair weather conditions is moved to an altitude of 1,000 feet, about 1 inch of mercury must be added onto the reading. The barometer readings at the two locations should be the same if there are negligible changes in time, horizontal distance, and temperature. If this were not done, there would be a false indication of an approaching storm at the higher elevation. Aneroid barometers have a mechanical adjustment that allows the equivalent sea level pressure to be read directly and without further adjustment if the instrument is not moved to a different altitude. Setting an aneroid barometer is similar to setting an analog clock that is not at the correct time. Its dial is rotated so that the current atmospheric pressure from a known accurate and nearby barometer is displayed. No calculation is needed, as the source barometer reading has already been converted to equivalent sea level pressure, and this is transferred to the barometer being set, regardless of its altitude. Though somewhat rare, a few aneroid barometers intended for monitoring the weather are calibrated to manually adjust for altitude. In this case, knowing either the altitude or the current atmospheric pressure would be sufficient for future accurate readings. The table below shows examples for 3 locations in the city of San Francisco, California. Note the corrected barometer readings are identical, and based on equivalent sea level pressure. Barometers and atmospheric pressure calculations. When atmospheric pressure is measured by a barometer, the pressure is also referred to as the barometric pressure. Assume a barometer with a cross-sectional area A, height h, filled with mercury from the bottom at point B to the top at point C. The pressure at the bottom of the barometer, point B, is equal to the atmospheric pressure. The pressure at the very top, point C, can be taken as 0 because there is only mercury vapor above this point and its pressure is very low relative to the atmospheric pressure. Therefore, one can find the atmospheric pressure using the barometer in this equation, PATM equals ρgh, where ρ is the density of mercury, g is the gravitational acceleration, and h is the height of the mercury column above the free surface area. The physical dimensions of the barometer itself have no effect on the height of the fluid column in the tube. In thermodynamic calculations, a commonly used pressure unit is the standard atmosphere. This is the pressure resulting from a column of mercury of 760 mm in height at 0 degrees Celsius. For the density of mercury, use ρhg equals 13,595 kilograms per cubic meter, and for gravitational acceleration use g equals 9.807 meters per square second. If water were used to meet the standard atmospheric pressure, a water column of roughly 10.3 meters would be needed. Standard atmospheric pressure is a function of elevation. Note 1 torr equals 133.3 pascals equals 0.03937 in Hg patents. US 2,194,624. A. Titterington, Jr. Diaphragm pressure gauge having temperature compensating means, issued the 26th of March 1940, assigned to Bendix Aviat Corp. U.S. Patent 2,472,735. C.J. Ulrich Barometric Instrument. U.S. Patent 2,691,305. H.J. Frank Barometric Altimeter. U.S. Patent 3,273,398. D.C.W.T. Sharp Aneroid Barometer. U.S. U.S. patent 3,397,578 HA-CLUM motion amplifying mechanism for pressure responsive instrument movement. U.S. patent 3,643,510 F-Lissau fluid displacement pressure gauges. U.S. patent 4,106,342 O.S. Sormunen pressure measuring instrument. U.S. patent 4,238,958 H-Dostmin barometer. U.S. patent 4,327,583 TVG Moto weather forecasting device.